episode of Chemistry, where we're finally getting involved with the topics that aren't just little small expansions onto what your first level of chemistry course's content is. We're finally getting into some of the new stuff. What a moment for us all. What a moment. As always, you can find links to the slides that are on the screen right in front of you and the notes to follow along just beneath this video. You're welcome. Let's get into it, shall we? This is Thermochemistry Part 1, split into two sections: enthalpy, exothermic, endothermic reactions, Hess's Law, and calorimetry. Yes, some of those words are familiar, some of them aren't. Let's dive into it, shall we? Heat versus temperature. Just a couple terminology things that if your teacher wasn't so intentional about labeling these words in your first exposure to chemistry, you might have thought they were the same thing. Temperature, of course, is the measure of the average kinetic energy of the molecules in whatever you're looking at. Heat actually isn't even a measurement of the energy within something. It's actually the measurement of the energy transferred between two substances. Very critical terminology that we're going to utilize later on in our questions at the end. Heat is the assessment of the transfer of energy, not the energy of the sample itself. Very important to note. Very important to note. Change in enthalpy. This might be familiar to you. I know that I mention it in my honors chemistry course whenever I'm going over it. However, I'm not really going into all the details about it. Really, I'm just talking about the sign and how this is associated with an exothermic versus endothermic process. But change in enthalpy, also known as delta H, is all having to do with the energy that's associated with the bonds that we are breaking and making. And this is a pretty intuitive, logical process. If I've got two things that like being together, then logically it's going to take energy for me to break them apart, which is why breaking bonds is always an endothermic process. Naturally, when two things come together, their instability, that potential energy that was keeping them from being as happy as they could possibly be, is released whenever they become stabilized by this new bond. Therefore, that is always an exothermic process. So the overall change in enthalpy that we see is the relationship between how much energy it takes to break and how much energy is released in the bonds that we make. Man, I'm a poet and I don't even know it. That's what is actually determining whether it takes energy to make a reaction happen or energy is released when that reaction occurs. So here we have in this reaction, it's just me spewing out the same words we just said, right? We know that in every reaction we are breaking what is on the left, we are making what is on the right, as long as this is a reaction that is going in one direction. Oh my gosh, that's going to be such a curveball when we start to shake that reality up. So in an exothermic reaction, more energy is released from the product side than what it actually took to break what is on the reactant side. Whereas an endothermic reaction, of course, is the precise opposite of that. It takes more energy on the left than is released on the right. And so we can see this as well echoed in graphs. And these are just some basic charts you can look up on the good old Google when you Google exothermic versus endothermic. In an exothermic reaction, the potential energy inside of the reactants is going to be higher than the products because we release energy along the way. Whenever we formed those products, they release energy. And in an endothermic reaction, it takes a whole bunch of energy in order to break those initial bonds, which of course is stored in the products and not releasing as much on the other side. And as always, most reactions require a little bit of investment of energy in the beginning as well. This, of course, is the activation energy. And so whenever you're looking at the peak of this graph, that is what is known as the activated complex. The analogy that I always use with this is, how do you flush a toilet? You can't just tap the handle. You have to push that handle past the point of no return in order to make the magic happen in your porcelain throne. So, you have to put in enough energy to get over the hump. But once that boulder gets to the top of the hill, it's coming down. That's when the reaction happens. And so, change in enthalpy, of course, is the overall change in energy of the reactions we are looking at here. In an exothermic reaction, we see a decrease in energy overall in the reaction. Right? Of course, we on the outside are feeling toasty warm because the energy is being released out towards us, but this is a negative delta H, a negative change in enthalpy of this reaction, whereas an endothermic reaction is a positive change in enthalpy. And we also kind of spoiled the plot here a second ago. Just moving my beautiful face out of the way so you can see that catalyst definition there. It is a misconception that a lot of teachers, it's your teacher's fault. It's never your fault. Your teachers may have taught you wrong. I remember when I was in high school, it wasn't until I got to college that I actually learned the truth. Mrs. Samuelson, why did you lie to me? Catalysts don't just lower the activation energy. They don't just straight up say, hey, it all of a sudden costs less to do this reaction now, right? If that were possible, my goodness, the possibilities. Instead, what catalysts do is they actually provide an alternate pathway. It's like you got a path through the woods, and then all of... You ever see that movie Shang-Chi? The Legend of the Ten Rings? Man, that's one of the most recent actual good Marvel productions out there. Don't even get me started on Multiverse of Madness. What a terrible cinematic experience, but Shang-Chi, solid. You know they're going through the woods, the bamboo forest, to get to the magical village. And all of a sudden, these new pathways are appearing. And those happen to be shorter pathways and going through the bamboo itself. And of course, I know that the bamboo is a very violent forest. This isn't the most perfect metaphor, but this all of a sudden just popped into my dome on how to visualize this. It provides a new pathway that does require less energy than the original pathway. I don't have to brush the bamboo to the side. The bamboo opened up for me and created a shortcut for me. And that required less energy to make that happen. That's what a catalyst does. Enthalpy of formation. Going in line with the logic of what delta H was a second ago. This is just how much energy is released or required when 1 mole of a substance is formed. Which you'll see on this table before us, these are all constant values, right? The amount of energy that it takes or releases when something is formed is mostly factual. I'm sure there's some variables that you could throw into the mix here that might change this a little bit. But it's going to be an intensive property. And so you'll notice that the vast majority of these values are negative. Why? Because when bonds are formed, energy is released. And so the fact that some of these are positive is telling you that the process of making it is not a spontaneous process. This is something fighting the laws of nature, or perhaps the bonds that we have to break in order to form these compounds, such as C2H2, when carbon is naturally existing on its own, H2 is existing as H2, right? It takes energy to break that bond in H2. So it's very interesting to look at some of these values where some of these feel like they should naturally exist, and sometimes we're fighting the laws of the universe. That's all man is. Just fighting the universe. When will we learn that we are the poison? We're getting dark here. Not listed here is that the delta HF for a pure element is defined as 0. That's very reminiscent of the oxidation state of elemental numbers in their pure state are going to be 0. Essentially saying that it takes no, or releases no energy and takes no energy to form something how it naturally exists. So, something like H2, for example. However, we know that there's a bond between those hydrogen atoms. Therefore, it's going to take energy to break that bond. But that's a different conversation. Let's get into assessing the change in enthalpy of a reaction. Well, change in anything is always where you ended minus where you started. That's logical, right? Change in anything has always been that. And so when I'm asked to find the delta H of an overall reaction, all I do is I find the total energy released by the products minus the energy that was required to break the reactants. Because that's what we're doing. We're making the right, we're breaking the left. So let's get into an example, shall we? We have the combustion of ethanol. You remember that whoosh bottle that you did in class? Oh, we were so young. We were so naive. Oh my gosh. What a sweet time. Ethanol goes boom boom in the big bottle. And of course every combustion reaction making carbon dioxide and water for us. Well, all we're doing is we're using the values from this chart a couple slides before. We see ethanol is on here. Ethanol, when formed, releases 277.7 kilojoules per mole. But we're not forming ethanol in this reaction. We're actually breaking it up vigorously, aggressively. So that is actually going to take energy. The amount of energy that's released from its formed is the exact opposite in sign of the amount of energy it takes to break this compound. So if we are breaking ethanol, instead of releasing 277.7 kilojoules, it's going to require 277.7 kilojoules. And so we're looking at this reaction. And of course, we're factoring in the coefficients from the balanced equation as well. But you might notice something. Where is O2 in this work that we are solving for? In this reaction, we've got 2 carbon dioxides plus 3 waters minus the reactants, ethanol, and 3 oxygens. But if I'm looking here and I'm using these values from this chemical equation, well, my goodness, O2 is not on this chart. Why? Because it is the element in its pure state. Therefore, not mathematically relevant here. And so all I'm doing is I'm adding together the reactants, and of course those values are here as well. Where are we at? Water over here, and also carbon dioxide over here on the left. And also notice that we've got different values depending on the state of water, whether it's a liquid or a gas, and so just pay attention to the reaction here. We see that our reaction is liquid water. I know one thing whenever I do this demonstration in honors chemistry, I always point out the fact that, hey, there's liquid water in the bottom of this bottle. And yes, we could boil it out and make it into water vapor, but that's not what the reaction does, right? It typically is going to stay in its liquid form. And so pay attention to that. If you're given a chart of constant values, don't mess it up. These are the gimmies, right? They are giving you all the values. All you have to do is products minus reactants, but also reflect how many there are. And so this first line right here where my cursor is, this is simply assessing the carbon dioxide and the water, the products, because that is going to be the left side of my mathematical equation here. So 2 times the carbon dioxide, 3 times the water. Our products are releasing 1,644.4 kilojoules. But how much did it take to break our reactants? Our reactants are 277.7 kilojoules, right? Understand that we are going to throw that minus sign in front of the reactants. Even though this chart says that ethanol releases 277.7 kilojoules when it is formed, we are not forming it here. We are breaking it here, which is why it is going to require 277.7 joules or kilojoules to break it. So it is a flipping of the sign. But notice that O2 doesn't actually contribute here because O2 is a pure element, an element in its pure state. Therefore, mathematically, 0. And so at the very end, we have reactants minus products. Sorry, the exact opposite. My goodness, scratch that. Products minus reactants, and we get an overall delta H for the reaction in negative 1,366.7 kilojoules. Is this reaction exothermic or endothermic? And this goes back to your beginner chemistry, factual, conceptual knowledge. If the sign of delta H is negative versus positive, what does that mean? Well, we know what combustion reactions do. They release a lot of energy, so this should just all confirm itself. A negative sign means it is going to be an exothermic reaction. The energy released from the new bonds formed is significantly greater, or just greater, than the energy required to break the reactants. But this is, if we look at the balancing of this reaction, this is how much energy is released when exactly 1 mole of ethanol is combusted, right? That's what the balancing of the equation tells us. That's what the coefficients of the balanced chemical equation tells us. Stoichiometry, wink, wink. But what if you don't have 1 mole? What if this question instead said, what if you only have 10 grams of ethanol? Do I really have to plug it all in? Absolutely not. Because what you just found is an intensive property. This is how much energy, or actually, sorry, this is an extensive property. But what I'm saying is that 1 mole will always release this amount of energy. But of course, it's an extensive property because we're changing how much ethanol is actually present. But what I'm saying here is that this amount, this negative 1366.7, will never change, provided you have 1 mole. So what if I just find out how many moles of ethanol I have and just multiply it by this value? Well, that's exactly what we're going to do. And this is what is known as the molar heat of combustion. How much energy is released per mole. And so all I have to do is 10 grams of ethanol divided by the molar mass, which is 46.08 grams. That's 0.2170 moles. and I multiply that by the constant value that 1 mole will release, and that will give me the energy that is released by this specific amount of ethanol, an extensive property. But the molar heat of combustion, how much energy is released from 1 mole, of course, is an intensive property. But that's also because you only have 1 mole. You always have 1 mole. So, just trying to throw some terms in here, okay? Sorry, it's early on a Sunday morning. Woke up fresh, haven't had my coffee. In fact, I've never consumed coffee in my life. Think about that. Now let's go into a new topic. Bond energy. James Bond energy. Man, that last James Bond was so bad. Daniel Craig is I may get canceled for saying this, but Daniel Craig is daddy to me. In a completely appropriate and respectful sense. But my goodness, that last movie was an abomination. And it's not Daniel Craig's fault. Okay? It's the big Hollywood producers up there. Don't care for him. What were you thinking? Rami Malek, great performance. Daniel Craig, great performance, but I didn't feel like James Bond was there. I felt like it was James Bond's 92-year-old papa. And the script, absolute abomination. But hey, here we are. I've been sitting on that for over a year now. Close to a year now, right? And it's just all coming out. This is very emotional. Every time I see the word Bond. And of course, being a chemistry teacher, it's a dark reality for me. Anyways, Bond energy. Same exact logic. And in fact, it is the same sign we are solving for, delta H. And yet, it is a different way of doing so. We are assessing the energy that is within a bond because, of course, energy is released when a bond is formed, but it takes energy to break bonds, which means there must be some pent-up energy within those bonds themselves. And I really like problems like this because it has you factor in exactly how many bonds are there. So it's tying in a bunch of concepts here. And so our reaction here is the energy used to break reactants bonds minus the energy released from bonds formed. Because this is inherently what these signs are. It should be a positive value of energy here, because remember, a negative value means energy released. A positive value used to break the reactants bonds, and a negative value released from these bonds, because we're not going to have a negative bond energy. There's always a positive amount of energy here, right? And so, this negative sign in front of me here is always going to flip the bond energy whenever we release it already for us. And so it's sort of the opposite thinking of what we were doing up here. It's doing some of that work for us. And so this equation, very, very simple. And pardon me, I couldn't get a double line on here on the good old Google slide, so a little half arrow will do here. So it's sort of the opposite of products minus reactants, but the signs do all the work for you, which is why I think this is actually easier. So the energy used to break the reactants bonds minus the energy released from the bonds in the products. So we know that we are always breaking here on the left. And when we were talking about enthalpy just a few slides ago, right, elements in their natural states don't have values here. But they do have bonds, and so the values aren't zero for this concept here. So we have to factor it in. There are 2 hydrogen molecules in this equation, 2 moles of hydrogen molecules. Well, in every hydrogen molecule, there's a single bond between the 2 hydrogen atoms. So there's 2 of these. Which means I have to put in enough energy to break apart 2 of those hydrogen molecules, which of course is going to be twice the value of 436. And a double bond, of course, will have more energy than a single bond, which is why I have to put in a little more energy, but there's only 1 of these. But in every water molecule, there's actually 2 of these hydrogen to oxygen bonds, because oxygen has a bond on either side of it here. And there's also 2 of these molecules. So let's get into the math here. Very, very simple here. We're just going to start with the energy that it takes to break those bonds, which will be a positive value, energy that we have to input into the reaction, and then subtract that from the new bonds formed in the product side, and we are going to still be able to determine whether or not this is an endothermic or exothermic process, because we're still calculating for delta H. This is just bond energy as opposed to our enthalpy of formation that we talked about just a second ago. So factor in those coefficients, factor in how many bonds are in the molecule, and this is still a fairly simple process. I loved when these questions were on AP practice tests or the actual AP test itself, because they give me the table of values, right? How do you mess that up? That's just you plugging and chugging into the calculator from knowing a very basic equation. I love when those pop up. Easy peasy. But Hess's Law, something brand spanking new. There's a lot of words on your screen here, but this is really when Miss Grider, back in my 8th grade Algebra 1, was first introducing the system of equations, substitution, and elimination. Scrumptious mathematical concept. So applicable. But you definitely weren't thinking that at the time of learning it, right? And so if you can take an overall chemical equation and break it down into the individual steps that make it, and we know how much energy is released or required for each individual step, well, then it stands to reason that the overall equation will be the sum of its parts. The sum of the parts equals the whole, says the old man in the lighthouse on a rainy night. But what if the steps themselves don't just smush together? In math, you had to make adjustments. You had to multiply one equation by -2 in order to cancel out the x's or the y's properly in order to smush them together. This is no different. We can multiply a step by an integer, and therefore it would multiply whatever the energy that is released or required for that step by that integer. Conversely, we can also flip the reaction entirely, or that step specifically, and it would therefore flip the sign of the equation. So what Hess's Law is it is a series of simple steps in order to combine them together to form an entire equation. We have the overall equation: carbon plus 1/2 a mole of oxygen makes 1 mole of carbon monoxide. That's the equation we are forming. And it is broken down into 2 steps. Carbon plus O2 makes CO2. Carbon monoxide plus half O2 makes CO2. And we have the enthalpy, that is the energy released from each of these steps. So we need to figure out how to smush these 2 reactions together to make what's up here. The question is, calculate the overall delta H for the reaction. Well, let's look at some things that are non-negotiables. This is how I visualize this. Some non-negotiables. I need to end with CO on the right. Well, the only equation I have out of these 2 that has CO is the bottom one. And CO is on the left currently. So what do we have to do? Non-negotiable. Flip it. We're going to have to flip that equation. But then the other thing you have to consider is, what like things do we have in both equations that need to be gotten rid of? We have the CO2s, we have the O2s that are going to cancel out in some degree. Because if you have the same thing on the left as you do on the right, then they will cancel out. So the fact that I've got both of my CO2s on the right-hand side of the equations, when there's no CO2 in the overall, should tell me that something is going to have to be flipped, no matter what. Same for the O2s. I need half of an O2, when right now I've got 3/2 O2s on the left-hand side of the equation. So something's going to have to be flipped. Non-negotiables. And so in my head, if I flip reaction 2, that is going to cancel out everything that I need. And all you have to do is add those pieces together. We're making no changes to reaction 1. So -393.5 stays the same. Reaction 2, however, we are flipping the sign. Therefore, it will go from -283 to +283. And when I smush those values together, I just get -393.5 plus 283 equals -110.5. A very, very simple mathematical process that I feel is pretty logical. However, this is as simple as it gets. We made one adjustment. That's all we had to do. And I remember getting challenge problems like this in AP Chemistry. I never saw an especially challenging one on like an actual AP test. But 3 reaction examples are definitely possible, right? But I wouldn't expect super, super challenging ones, because a lot of these end up being multiple choice questions where you have to be able to do the conversions pretty quickly. And so you're not expecting things where it's like, oh, I have to multiply the top one by 6 while flipping the other one and multiplying it by 3. Like, nothing like that. It's usually a flip and a multiplication. Maybe 2, right? That's what you're looking at here. So let's look at this 3 reaction example. Same question. Calculate the total delta H here. And let's once again consider our non-negotiables. And that's what these notes to yourself, even though I put those notes there for you. Inception, Leonardo DiCaprio. Let's do some non-negotiables. Our reaction is 2 carbons plus hydrogen gas, 1 mole of it, makes C2H2, which I think is acetylene, I think, from your good old blowtorches. Well, would you look at this? The only reaction that has C2H2 is on the reactant side. So that guy's going to have to be flipped no matter what. That's the first thing that I'm looking at. And then also, I got all these O2s and CO2s in these reactions, yet I got none of that in the overall equation, which means those have to cancel themselves out. So what alterations can we do? Well, in flipping this first reaction, we've got 2 carbon dioxides and 1 water coming over here. And looking at these other reactions, there's only 1 water to begin with. So the waters are taken care of. But the CO2s, however, not. Because I'm going to have 2 carbon dioxides over here on the left now once I flip this. But I've only got 1 carbon dioxide here. But the reason why this is fine and dandy is because this reaction, too, only has 1 C. But the overall reaction has 2 C's. So we have flipped reaction 1, and we are now in the understanding that we have to multiply reaction 2 by 2. That's French for 2. Now, if we do all of the math there, we see that all of the O2s would be canceled out as well. Because we'd be flipping our 5 O2s to the right with our initial change of flipping reaction 1. That's 5 over 2. And this multiplied by 2 is going to be 4 over 2 O2s, and I've got the other half O2 right here as well. And all of those are remaining on the left. So all of my O2s are canceling out, all of my CO2s will be canceled out, all of my H2Os will be canceled out, and I've got the appropriate overall reaction. And so, we've reflected all of these changes on this slide here. And you'll see that when you smush it together, you get what the intended result is to be. And so, in flipping the first reaction, it just goes from negative to positive. In doubling that second reaction, we've doubled the enthalpy value of that reaction. And reaction 3 stayed the same. Didn't have to touch it. That was pretty cool. And then throw it all together. And would you look at that? This reaction requires energy in order to happen. Well, didn't we bring to light that fact that acetylene requires energy to be made? Egad! And we proved it with this series of steps here. That's pretty cool. That's pretty cool. It's all coming back. Calorimetry. In the first level of chemistry, the extent in which you typically go over this is Q is equal to MC delta T. You put a hot piece of metal in a cool glass of water and you watch the heat go from the high to the low. Heat only travels in one direction, from the hot object to the cool object. But this is AP chemistry. We're all grown up. Let's get a little bit fancier with it. When you dissolve stuff in water, heat is released. Let's talk about why. 3 things happen simultaneously when this occurs. When you dissolve something, typically we're looking at these ionic compounds when they're dissociating. Ionic compounds, as we talked about in the last video actually, when we talked about bonding, there's a great deal of energy between them. They like being next to each other. So it takes energy to break that ionic substance up. However, we are paid our dues by the end of this process. So it takes energy to break it. It also takes a small amount of energy to take these water molecules that are all next to each other and put a little bit of gappage between them to separate them. Right? We're not splitting the water molecules, but we are increasing the distance between the water molecules. Why? Because the ionic species had to go somewhere. I understand that a lot of these mathematical equations, we go, assume no change in volume, when quite literally, we have to put these pieces somewhere, right? A lot of times they don't take up much volume, but they do have to go somewhere. They can't just embed themselves within water molecules, no. They take up space themselves. However, when these little positive and negative itty-bitties then become attracted to the positive and negative dipoles of the water molecules, that releases energy. And so a little terminology here, steps 2 and 3 here, is also called hydration energy. Because the energy released from step 3 is always greater than the amount of energy it takes to separate the water molecules. Why? Because you have water molecules that, yes, are very polar bonds, but they're not total poles. They are not total positive and negative. Whereas the ionic species that you're bringing into the mix here are total positives and negatives, which are inherently going to be a stronger connection and attraction than what the water molecules were experiencing themselves. That's the difference between dipole-dipole interaction and ion-dipole interaction. But the question is, what's the differential between steps 1 and 2 and 3 combined? That's when you look at what is called the enthalpy of solution. And it is an exothermic process. If your teacher has ever asked you to make solutions in the lab, sometimes when you put stuff in water, you can actually feel it get a little hot. It's not usually that much heat when you're working with that small of solutions. But you can have a pretty hot solution, and that's pretty cool. Vapor pressure, we talked about this in the last video as well. The higher your vapor pressure, the more likely for a substance to enter the gaseous phase. I always think of it like the molecules trapped underneath the surface of the liquid trying to break out. And if they're hitting harder, meaning that they are hitting with more pressure, then they are more likely to bust out and become a gas. So this is going to be a topic that is not talked about too much, but it is definitely going to come into play in our math a little bit later on from here. Then we also have just new applications of terminology that we might already know, right? We know phase changes occur, and this phase change diagram should look pretty familiar to us with the 3 slopes, right, and the 2 horizontal lines. Well, those horizontal lines represent phase changes, where I'm still adding energy, yet the temperature is not increasing. Put that in your head. You're adding energy, and the temperature is not changing. Why? Well, it's because there is a difference in not kinetic energy, but potential energy when transitioning from solid to liquid and liquid to gas, right? And of course, this chart can go both ways. I can both add energy or remove energy, and it would have the same change, but opposite. And so, we are looking at enthalpy once again, that lovely delta H. Enthalpy of fusion is how much energy is required to melt a solid, and of course, if we were to flip it, the energy that is released when we form a solid from a liquid. And enthalpy of vaporization, this one should be pretty easy to deduce because evaporation, another word for it, is vaporization. So it's the amount of energy required to completely evaporate a sample of liquid. So now, with this in mind, this is going to make our Q is equal to MC delta T problems a little more varying. If you'll think back to your first level of chemistry, you probably only had questions where you had water being heated. But did you ever have questions where you were transitioning from solid ice to liquid water, and perhaps even then liquid water to water vapor, steam? You probably didn't. Because it's just yet another layer to add on the top. It takes energy to overcome those phase changes. This chart proves that. But the temperature's not changing, and that's what you have to wrap your brain around. There's a difference between potential and kinetic energy. And so our problems, the equation is still the same. Q is equal to MC delta T. But what happens when there's no delta T? What's the problem? What's the equation for that? Well, there's still energy going in. And there's still the amount of substance to be worrying about. Well, let's get a question here. 2 moles of water at negative 30 degrees Celsius is absorbing energy until it is 140 degrees Celsius. My oh my. Calculate the amount of energy in kilojoules needed for this change. Did you know that substances can have different specific heats depending on the state of matter that they currently are? That's kind of spicy. So water has a specific heat when it's solid, liquid, and gas. What a lot of you might try to do right away is just take the mass of this water species and go, oh, the delta T is 170 degrees. I'm going from negative 30 to 140. But that's not the full story. Because water is changing over time. there is a point on this chart where I'm putting energy in and the temperature is not going up. And so if you just did Q is equal to MC delta T and the delta T was 170, that's not accounting for the energy that's being absorbed here and here. So actually this question is 5 steps. And it's also involving the heat of fusion and the heat of vaporization. Now pay attention to these units and how they're different from the specific heats. Because Q is equal to MC delta T is contingent upon how large your sample is. Well, heat of fusion, heat of vaporization is no different, right? If I throw an ice cube versus a glacier in my front yard, yes, I understand the glacier is going to take longer to melt. They both melt at the same temperature, but there's just a whole lot more ice in the glacier in order to melt. But notice the units here. Kilojoules per mole, kilojoules per mole. How much kilojoules it takes to overcome the phase change per mole, as opposed to the specific heat, which we are involving grams. But also notice that this question was super nice to us. It gave us both the moles and the mass. This is why questions like this can very easily be implemented into a multiple choice section, because they're making the math easy on us. And so actually, when I said that this question is 5 steps, there are 5 calculations we have to do. We have to get the ice ready to melt, meaning bring it to the melting point, negative 30 degrees Celsius to 0. That's a Q is equal to MC delta T problem. But number 2 is something new. The energy required to go from solid to liquid, and that's where we involve the delta heat of fusion, the delta H of fusion. How much energy is required to melt a sample of ice? Then it's another Q is equal to MC delta T, 0 to 100. Real quick. But then once again, it's that new terminology, delta H of vaporization. How much energy does it take to move from the liquid to the gaseous phase? Notice it's a lot more energy. Why? Because I'm overcoming the potential energy of the liquid. Gases are crazy. They have way more kinetic energy. Why? Because we're overcoming the potential energy that they had stockpiled in the solid and liquid phases. And then, of course, once we are completely a gas at 100 degrees Celsius, going from 100 to 140, let's break it down into multiple steps. Step 1 should not look weird to us. Q is equal to MC delta T. This should look simple. And keep in mind that the question did originally say that it wants it in kilojoules, right? We're working with a lot of energy here, so kilojoules is typically the way to go. So step 1 should not look unfamiliar to us. We've got the M, the amount of water. We've got the specific heat of solid water, not liquid water, and the temperature change of 30 degrees. And I know I wasn't too good about the sig figs here, but we're also compiling 5 steps into one final answer, so I don't want to really round until the very end. So anyways, I've converted the joules at the end of this step to kilojoules by simply dividing by 1,000. Then we also have to put in the energy to convert solid ice to liquid water. Once again, the terminology for that is delta H of fusion, the heat of fusion. The energy required to go from the solid to the liquid phase, and that's based on the moles. Well, they gave us all of the values that we need. It is a constant value. For every 1 mole of water, it will take 6.01 kilojoules in order to overcome that. And because we have precisely 2 moles of water, simply 2 times that value is how much energy that step is going to require. Step 3 should look very familiar to us because we were almost always working with liquid water in our first level of chemistry. So this 4.184 might even be, we might even have it in the back of our brain still because it's something that we recall. So this, once again, exact same as step 1. The only difference is the specific heat. And of course, the quantity of temperature change. And then divide by 1,000 at the end. That's our kilojoules of energy required. Step 4 is our heat of vaporization. It should look very similar to step 2, but using that heat of vaporization value instead of heat of fusion. Step 5, very similar, but using the water vapor constant specific heat for water instead of the liquid. How much energy is required to elevate 1 gram of that substance by 1 degree Celsius. That's what we're looking at here. And then when I combine all of the steps, right, this plus this plus this, plus our 2 values here, 81.4 and 2.70, we get 113.43 kilojoules required to make this process happen. The math is simple. Each individual step is easy. But will you know to account for all of the steps? That's the new addition to this kind of problem. Now let's get a little bit more chemistry. Right? Involve a couple more topics, because what I'm trying to do with all these notes and these sample questions that we're going to do here in a second is try to use the questions that involve multiple topics and concepts that you already know. Right? That horizontal thinking, right? We're not going to just ditch a topic the moment that we are done learning it, right? We apply it to the future. A certain material's temperature increases by 1.0 degrees Celsius for every 1,560 joules that it absorbs. That terminology right there is giving you multiple things. That is giving you the amount of the sample and the specific heat all in one. So it's a lot of information in just one sentence. A 0.1964 gram sample of quinone, whose molar mass is blah, 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 blah. They don't want you to calculate anything. Like, how nice is that? Was burned and the surrounding material's temperature increased from 20.3 degrees Celsius to 23.5 degrees Celsius. Find the molar heat of combustion, which is a fancy way of saying how much energy is released for every 1 mole. Well, we actually did this earlier with our ethanol question, and now we're applying it to calorimetry here. So, we don't have 1 mole of quinone. So, what we need to do is we need to find out how many moles of quinone this is at some point, but also let's figure out exactly how much Q is involved here in this step. And of course, that is going to be simply multiplying the constant that they gave us by the temperature change. Because they effectively gave us the specific heat and the mass of the sample all in one, so I don't have to worry about this specific mass or the actual specific heat. It's this sample, which could be 100 grams, could be 1,000,000 grams, whatever it is, goes up by 1 degree when this amount of energy is absorbed. Can't dispute it, right? So this effectively tells me that there's roughly 5,000 joules absorbed here, or released by the quinone. And this is the concept that we're tying in. The amount of energy absorbed by this material, where did it come from? There's only one source here. We're not talking about the sun beating down on it. It is released from the combustion of this quinone. Quinone. Kind of like that better. Quinone. So, the amount of energy absorbed is equal to the amount of energy released. That's the concept here. And that shouldn't be new either. That should be a pretty elementary concept for us here. So anyways, we've got our moles here by simply taking the amount given to us in the problem divided by the molar mass, also provided to us in the problem, and then I simply take our energy absorbed divided by the amount of moles here, and that will give me how much 1 mole is released. That's simple unit dimensional analysis, right? The amount of energy absorbed by this amount of energy released from this substance, I can use to convert that to what 1 mole would release in turn by taking the energy released by this amount divided by the amount that there is, and I get a really hefty amount of joules, which is why this question wants it in kilojoules. That was a really convoluted way of explaining that, right? But if you are writing out your units, joules over moles, that's exactly what the unit of molar heat of combustion is. How much energy is released per mole. So doing that operation will give you the molar heat of combustion. A lot of people get caught up in units, but units are telling you the full story. The units of your result, how much energy is released from every mole. That's joules over moles. So put joules over moles, and you get the answer, converted to kilojoules. Divided by 1,000 here, and we get our kilojoules. So we're looking at 2750 kilojoules. Rounded, of course. Boom! Pretty easy. Use those units. Let's finally get into some sample multiple choice and free response questions. It's been a long talk already. In all honesty, the topics discussed today are more inclined for multiple choice questions. Free response, I'm actually pretty thankful if one of these topics appears on a free response question. And more likely, it's that this is one part of a free response question. But either way, let's tackle it. We've got 1.50 grams of NaNO3 is dissolved, right? We're making a solution causing the temperature increase by 2.2 degrees Celsius. Very reminiscent of the enthalpy of solution topic we just talked about a few minutes ago. The density of the final solution is found to be 1.02 grams per milliliter. Which of the following expressions will correctly calculate the heat absorbed by the water as the sodium nitrate dissolves? Remember, as something dissolves, there's that three-step process that is going to be an exothermic process and cause the solution to heat up. Assume the volume of the solution remains unchanged. And this question is a little bit trickier than actually meets the eye. In fact, if we didn't have the conversation that we had today, you might gravitate towards one of these answer choices really quickly. And that answer choice is A. And let's think about why that is. Because calorimetry before today was simple. Q is equal to MC delta T. I've got my mass of water here. Remember, the density of water is just 1. So 25 milliliters is 25 grams of water. It goes up by 2.2 degrees Celsius. And the specific heat of liquid water is 4.18. So that would be the Q that the water is absorbing. But the problem with that is when you make a solution, you have the ionic substance that's dissolving, you have the water, and when one dissolves in the other, they effectively become one. We talked about those attractions to one another. How the water molecules literally will separate, not the molecules themselves, but the distance between water molecules will increase so that the ionic species can slide in there. They become one. Not literally bonded, but they're attracted to each other. So this 25 milliliters doesn't tell the full story. Why did they include the density if it wasn't meant to be used? That's the question you have to ask yourself. And so when you're looking at the equation Q is equal to MC delta T, which of course is the appropriate equation here, where does the density get involved? It's the mass. Because this 25 milliliters is not the same mass that we have at the end. When I add these grams of NaNO3 to this, we have a new mass to this solution. And so the equation that you're looking for is D is equal to M over V, one of the very first equations that you look at in chemistry. How do you solve for mass? And that is going to be D times V. So what they want you to do is 1.02 times 25, and then involve your specific heat and your delta T. And so our equation here is what has all of these numbers in this question multiplied together. And that, of course, is D. It's a little bit trickier than meets the eye. If you look at B and C, they don't really make sense if you think about it. Randomly dividing by the mass of the ionic compound, it doesn't make sense. There's no equation that we have that does that. And then dividing by 1.02, it might be a decent choice to look at here, but then you think about what the density equation is, and it doesn't make sense, right? This is effectively taking the mass divided by the density and solving for volume. Where is volume ever involved in Q is equal to MC delta T? So it doesn't make much sense. A, in my opinion, is the second best choice. It's where most people would go wrong with it, in my opinion. But we already explained why D is the correct answer here. So let me get my head out of the way for number 2. A student studies 2 solutions. Solution A has a volume of 100 milliliters and is at a temperature of 25 degrees Celsius. Solution B has a volume of 1,000 milliliters and is at a temperature of 22 degrees Celsius. So this guy is less and warmer. Solution B is more and a little bit cooler. Which of the following statements must be true regarding both solutions? Solution A has more heat than solution B. That answer choice is attractive. Right off the rip. A is warmer than B. But that's not what answer choice A is actually saying. I'm going to go back to the very first slide of this presentation. Hey! Heat and temperature are not the same thing! Heat is literally the transfer of energy. Does this question ever imply that heat is being transferred anywhere? No. So you can't just, quote, have more heat than something. So while that choice looks appetizing, it's because you don't know what the word means. We haven't even read the others yet. And A was already looking pretty good. But it's a bait. Don't fall for the trap. There's no heat being transferred here. You can't have heat. You can experience a heat transfer, but that's not even being talked about here. B, the specific heat capacity of solution A is greater than that of solution B. We don't know that. This question is not talking about how much energy or what the temperature change is after absorbing X amount of joules. It hasn't been said. This is just two solutions we pulled out of somewhere, some cabinet somewhere, and they have these details about them. We don't know why they have these details. We haven't talked about the before and the after. We don't know. And also the difference in how much stuff is here is such a big variable that B doesn't actually account for. If the solutions were to be mixed, heat would transfer from B to A. So already we've eliminated A and B. We haven't even read C and D yet. C is a hilarious answer choice. It is. If you're picking C, I laugh at you. The cooler thing giving heat to the hotter thing. Does that ever make sense? Is that ever valid? No. In fact, we've said it in this video here today. Heat only travels in one direction, high to low. It could only ever travel from solution A to solution B. So without even reading answer choice D, the answer is D, because A, B, and C don't make sense. Solution B has more thermal energy than solution A. And it's really hard to definitively say that, to be honest. It is simply the best choice here. But let's talk about why D is going to be accurate. It's because there's 10 times the amount of B. And the temperatures are so close to each other. Right? We know that thermal energy exists in these molecules. Whatever the compound is, it doesn't even tell us what it is. Energy is within each of these molecules. Their temperatures are very close, and B has 10 times it. So, there's a lot of energy in there, is all I'm trying to say here. To definitively say solution B has more thermal energy than solution A, personally, I want more information. But it's also the only valid choice here. Why did I include this? In all honesty, it's because of answer choice A. One little word that looks mighty appetizing. Do not get tripped up. Definitions are important in AP chemistry. Important for these questions. Couple more multiple choicers. And we're using the same information. When calcium chloride is dissolved in water, the temperature of the water increases dramatically. Molar enthalpy of solution? Ah! Which of the following must be true regarding the enthalpy of solution? Answer choice A, the lattice energy in CaCl2 exceeds the bond energy within the water molecules. Remember, when we're talking about this, it's 3 steps. It takes energy to break up the CaCl2. It takes energy to separate the water molecules from one another. And then energy is released when the Cas and the Cls get attracted to the waters. Right? Answer choice B, the hydration energy between the water molecules and the solute ions exceeds the lattice energy within CaCl2. Our change is an exothermic process. And answer choice B is literally saying that more energy was released than I had to put in to break up the CaCl2. Huh? Whereas answer choice A is saying that it took more energy to break CaCl2 than to break the energy within the water molecules? I'm sorry. Are we separating water molecules now? Are we literally breaking the bonds of water molecules? But they've thrown this chemistry terminology at me. Bond energy, I don't know what to do. You are not breaking water molecules here. You are disrupting the interaction between H2O and H2O, but you are not breaking an individual H2O. And that's a very important distinction with answer choice A. C. The strength of the intermolecular forces between the solute ions and the dipoles on the water molecules must exceed the hydration energy. Hydration energy is the terminology associated with steps 2 and 3 in that process of enthalpy of solution we were talking about. And this is never accurate. Or sorry, this is always accurate. Said the exact opposite. the energy of attraction between the absolute ions and the water molecules always exceeds the intermolecular forces of the water molecules themselves. C is always true. So why would it be the right answer in this specific context? So then we look at answer choice D. The hydration energy must exceed the strength of the intermolecular forces between the water molecules. This is always true. So looking at these two choices that are close to saying the same thing, right? The strength of the intermolecular force between the solute and the dipoles in the water must exceed the hydration energy. They do, but that doesn't tell me why this change occurs. Because the attraction between full positives and negatives is greater than partial positives and negatives. And then D is always true because the full positives and negatives always exceed the attraction between partial positives and negatives. C and D are effectively the same thing. And we've already did a little at answer choice B. Because this is the exact explanation for an exothermic process. A doesn't make sense given the context of the situation, and C and D are the same answer choice, effectively. They're not literally the same definition, but C and D are the same answer choice. So it must be B, because this is an exothermic process. Compared to CaCl2, what must be true regarding the hydration energy of CaF2? Well, my goodness, if this ain't the freaking Coulomb's law that we talked about last video, where the energy is related to two factors: the distance between them, the radius, and the charge. CaCl2 and CaF2 have the same dynamic. Calcium giving 2 electrons, and the anion receiving 1 electron each. So what's the difference between them? What must be true regarding the hydration energy of CaF2? Answer choice A. It would be greater because fluorine is smaller than chlorine. Because fluorine is a smaller atom than chlorine, it therefore can get a whole lot closer to calcium than chlorine can. That's very good. It's the exact definition of Coulomb's law that I'm looking for. But let's look at the other answer choices, right? It would be the same because the charges of fluorine and chlorine are the same. Fluoride and chloride. Well, that's just not knowing Coulomb's law's definition. Is two factors, two variables. Distance and charge. The second half of the sentence is true. The charges of fluorine and chlorine are the same. That's accurate. But it is not considering the other variable. It would be the same because hydration energy is only dependent on the IMFs present in water. I feel like this answer choice is not picked by a large percentage of test takers. I mean, not that the terminology hydration energy is thrown around too much, but when they use things like only in answer choices, doesn't it just like make you a little suspicious? But of course, our definition of hydration energy is contingent upon, yes, the energy required to separate the water molecules from one another, but also it's the resulting attraction afterwards, which of course would be contingent upon the charges and the distance of the molecules. Coulomb's law once again. So C doesn't make sense. It would be smaller because the molar mass of CaF2 is smaller than that of CaCl2. I like this as an answer choice. I think this is a good baiting answer choice. Especially coming off of last topic in last video, which was London dispersion forces, where yes, the larger molecules have more London dispersion forces. Why? Because they got more electrons. And so it's very common to associate that with mass directly, when mass doesn't tell the full story. And so it's not mass that is going to make your charges stronger here. And so the answer is A. The answer is A. Let's get into our free responses, shall we? The diagram above shows how the temperature of a certain covalent substance changes as heat is added to it. Notice these lines, right? This chart is telling the whole story here. Adding energy, we still got the same phase change diagram. This first line segment, very steep, a little more shallow, and then about the same slope. But look at these lines as well. Whole lot shorter process, whole lot longer process. Okay? Which is greater for the substance? The heat of fusion or the heat of vaporization? And how do you know? Well, we're looking at the chart. Heat of fusion, once again, is how much energy is required to go from solid to liquid. Heat of vaporization is how much energy is required to go from liquid to gas. This x-axis is energy. How much energy do you have to put in to make this change occur? Who has the longer line? Fusion, vaporization. I'm putting energy in, but the temperature is not going up because, remember, this energy is being used to overcome the potential energy, which means the energy of vaporization is going to be higher than the energy of fusion, which also is in line with the example problem we did earlier in this video. The vaporization was higher than the fusion. If additional heat is added to the substance, the line would continue at its current slope and never become horizontal again. Why is this? One, I'd like it's 2 points here, right? Current slope, never become horizontal again. Why is this? Well, it's because we're already a gas. This is a pre-AP question. This is an honors question. I don't even need AP to do this. It's a gas, right? We don't go above gases. We're not going to become another phase ever again if we are continuously adding heat. But also the other point is, why is it continuing at its current slope? Well, it's because specific heat is a constant. And even though the specific heat can be different at different states, when it's a gas, the specific heat is the specific heat. So it will maintain its current slope because the specific heat doesn't change as long as we are in the gaseous phase. But it never becomes horizontal again because we're not going to experience another phase change. Reading the graph above, a student theorizes that the specific heat capacity of the substance is greatest in the solid phase. Do you agree? Why or why not? What is the definition of specific heat? Specific heat is how much energy is required to increase 1 gram of substance by 1 degree Celsius. Therefore, a lower specific heat value means that I don't have to put in as much energy to experience a temperature change, whereas a greater specific heat value means I have to put in more energy to accomplish the same change. A student theorizes that the specific heat of the substance is greatest in the solid phase. Well, my goodness, could they possibly be drawing your attention to the steepness of this slope here? Meaning I only had to put in a small amount of energy to experience this great of temperature change? Well, that doesn't sound like a high specific heat capacity. That sounds like an incredibly low specific heat capacity, meaning that this substance, whatever it is, absorbs energy very readily. And it doesn't take much energy to accomplish a temperature change. So, no, I don't agree with this guy. Why? For the reasons I've been saying this whole time. We've experienced a good temperature change while putting in no heat. Virtually no heat. Whereas the distance between here and here is roughly the same as here to here, but I had to put in way more heat to go from the bottom tier of liquid to the top tier of liquid, right? Just before it goes to the gas phase. Gas we don't know the full story of, right? I mean, we could still look at the steepness of the slope. It's not as steep as solid. So no, I disagree with you, young student. You would fail your AP test, you idiot. Next question. A student designs an experiment to determine the specific heat of aluminum. Student heats a piece of aluminum with a mass of 5.86 grams to various temperatures and then drops it into a calorimeter containing 25 milliliters of water. So we got some basic Q is equal to MC delta T questions here. Just wanted to show you that, yeah, it can be pretty simple. I could give this question to my honors chemistry class, and I would feel pretty confident that they're able to do it. So yeah, let's go in the motions here. I like this question because it's tying in multiple concepts here, and you'll see what I mean. And also, it's showing you that this is an easier topic to experience on the free response question. So yeah, I want to take advantage of something like this appears on a test. Given that the specific heat of water is 4.18 joules per gram, and assuming its density is exactly 1 gram per milliliter, calculate the heat gained by the water. We're just solving for Q here. And so we've got the initial temperature of the water. We've got the final temperature of the water. That's the delta T. We've got that it's 25 milliliters of water, therefore 25 grams of water. I just plug and chug. This times that times that. and I get about 377 joules of energy. So this is where the concept of heat absorbed by the water is equal to the heat released by the aluminum. That energy came from somewhere, the law of conservation of energy. So B is calculate the specific heat of aluminum from the experimental data given. Why did I flip this negative? Because if this absorbed the energy, then this released the energy. Why does it not even matter? It's because the temperature change that aluminum is experiencing is a loss of heat. So it's going from the lower, in the mathematical sense, it's the lower temperature minus the higher temperature, which would be a negative value here. We're going to end with a positive value, no matter what. That's all I'm trying to say here. And so now we're just plugging in the values, and we're solving for C. So it's 377 divided by my mass and my temperature change, and I get a specific heat of about 0.782. An honors chemistry calculation, absolutely. Where do they go from here? Calculate the enthalpy change. This is kind of new. For the cooling aluminum in water, and all they want to do is find out if I've got 1 mole of aluminum, how much energy would that mole of aluminum release? Well, I don't have a mole. I've got 5.86 grams according to this problem. So if this amount of energy was released by this amount of aluminum, if I just simply multiply that mole amount, divide this energy amount by the amount of moles of aluminum that I have, then I get the joules per mole that I'm looking at. Once again, emphasizing the concept we talked about earlier in here. So I've got 0.217 moles of aluminum once I convert that, and 377 joules divided by 0.217 is 1,736 joules per mole. But this question did ask for kilojoules, so divide by 1,000, and we get 1.74 kilojoules, give or take. And another reason why I included this question is because of D. Part D. How basic is that? The accepted specific heat of aluminum is 0.900 joules per gram Kelvin. Calculate the percent error. They've implemented real-life scenarios into this free response question on how you could possibly screw up. But also part of your points are just you calculating the screw up, and that's pretty nice. I don't think I need to have to go into the percent error equation. Accepted minus experimental divided by accepted, or theoretical minus experimental, theoretical minus actual, whatever it is, but it's absolute value bars on the top of the equation. Multiply it by 100 at the end and you get your percent, 13.1% error. And of course, all of these mathematical questions in the free response section, they'll have a small window that you can fall into. So, I mean, I don't even know if they follow sig figs on the AP free response anymore. I don't even know. But I imagine there's a margin of error built in for these. Suggest 2 potential sources of error that would lead the student's experimental value to be different from the actual value. Just give 2 reasons. And these are pretty easy. Right? You're thinking about what you're doing. You're heating up your metal. You're dropping it in the cup of water that I'm sure is a top-of-the-line calorimeter and not a public-funded high school styrofoam coffee cup. What am I getting at here? Not all of the energy that is released by the aluminum is going to go into the water. You're going to lose some energy to the environment. Period, end of story. Right? What would that do? That would show that your aluminum is releasing less energy than it actually did. So that would throw off your calculations just a little bit. Secondly, what else could we say? Well, we could go off of user error from the very beginning. What if we didn't actually have 25.0 milliliters of water? What if the temperature achieved by the aluminum wasn't 109.1? What if the final temperature wasn't actually 26.8? I'm going to go more off of the water. What if I put in 26 milliliters instead of 25? I just read it wrong. Took it from the wrong meniscus. I was seeing double. I don't know. Either way, it would show that the aluminum wasn't releasing as much energy as it actually did. And so it would in turn make your specific heat values appear lower than what it was supposed to. Hence why our specific heat was 0.782 when it was supposed to be 0.900. Right? Very easy errors to assess. All in all, I know this is a pretty standard length video for us. It's a pretty long video. But the topics here are extensions upon stuff that we know. Pretty logical extensions. And I would be thankful for these topics to appear on an actual AP test, because in all honesty, these are not the ones you should be missing. I don't want to psych anyone out by saying things like that, but this is a good one to study for because it's a good set of concepts that I can bank on whenever it comes to the actual test time. But my goodness, what a journey it was! And I'm glad to be the one giving you this info. Corona Chemistry. Out.